Hello, welcome back. In this video, we're going to continue our study of electrostatic fields in materials, and particularly we're looking at the polarization of dielectrics. So let's get started. Materials consist of atoms, and in a simple model, these atoms can be considered to be a large collection of randomly oriented small electric dipoles. Let me draw that. So let's say we have a material, and let's say that the material is in free space. So out here is free space, and then inside here's our material. So randomly oriented electric dipoles, maybe like this. Okay, so we're assuming that our material is electrically neutral, like this. So I'm showing the electric dipoles, the materials. We're modeling we're modeling the atoms as electric dipoles. With an applied electric field external to the material, the dipoles may reorient themselves. So let's say I've got an electric field that points in this direction, external. I can apply an external electric field. A large number of them, or maybe even all of the atoms, will align themselves, causing an electric field internally from the dipoles. So now let me draw that. Let's draw the reorientation of these things. So inside that electric field, and again, remember we're saying that this material exists in free space. So now what's going to happen to the electric dipoles, I guess, let me redraw this with, yep, like that. When there's an electric field externally, the dipoles will align themselves to the electric field, and the positive charge will want to go this way, right, and the negative will go that way, like this. Alright, now this will cause an internal electric field, as we said in the previous video regarding conductors. This causes an internal electric field, and the total electric field is the superposition or the addition of the external and the internal electric fields. Now the distance from, really the positive should be in the center because the positive is the nucleus, but the distance from the positive center and the outer electron, or the valence electron, of the adjacent atoms is small. It's like on the order of 10 to the minus 10 meters. So what we can do is make an approximation and say that these two things cancel each other out, and these two things cancel each other out. These two guys cancel each other out, and so on. Of course, the material has more than 9 atoms, but I can't draw them all, right? And so essentially what we have is, again, because of the applied electric field, we have neutral material in between those dashed lines that I just drew, right, with the cancellation of the negatives and the positives. And then on the surface, there's no cancellation, and there's positive charge, and then there's negative charge. So now essentially what we have is something that looks like this, where we just have positive, negative, like this, and then this is neutral here. Right? And this charge distribution is called the polarization charge. and that creates a dipole in itself, right? So each one of these can be considered a dipole, and then we can add the dipole moments together. And remember, the direction of the dipole moment was from negative to positive, and so the sum of all of that we're going to call P and as a vector, and we're going to call that the polarization, not to be confused with power or lowercase p, which was the dipole moment. Now, in perfect conductors, there are so many free electrons that this happens and this balances out the external electric field and causes zero electric field inside the material. But for dielectrics, that's not true. There are not enough free electrons to balance out, in general, the applied electric field. And of course, in free space, the reorganization of atoms cannot happen, right? Because it's free space and there aren't any atoms. There aren't any materials, that is. So the individual dipole moments from each dipole obey superposition, right? And they add together and they make this polarization, P. And we're going to define it in something that looks similar to when we defined divergence and curl. We're going to define the polarization at a point, right? It's a vector field. And what we're going to do is we're going to take a volume around that point, shrink it towards zero, and add up all of the dipole moments through that point. So this is a lowercase p here. Okay, again, so P sub j is equal to Qj times dj, which is the dipole moment of the jth dipole. Right, so we're going to add up all of the dipoles around in a certain volume, vector addition, shrink the volume towards zero, and then we have the dipole moment at a point, and we call that the polarization. So let's discuss what the units of polarization would be. The dipole moment is coulombs times distance, and then we've got over cubic meters, right? And so this is coulombs per square meter is the polarization. And remember, we had something similar when we defined divergence and curl. Now, like Gauss's law, then, we can express the divergence of the polarization as a constant like this. So we can go back to how we derived Gauss's law, but we're not going to do that. And what we're saying here is the divergence of the polarization is a constant. It's related to this, what we're going to call the bound volume charge density. And so what we've got here in our material is the bound charges are charges that are not free to move around the dielectric material. They're caused by the displacement that occurs on a molecular scale during polarization. So without the polarization, they do not move. They're bound to the structure. But with polarization, they're displaced. And then, so again, this is the bound volume charge density due to the polarization. So this looks a lot like Gauss's law. And we've got a negative sign here, which we did not have for Gauss's law. And that negative sign is due to the fact that we're defining the polarization in the direction of the dipole moment, which is from negative to positive. So that's the reverse of how we define electric fields. And so we're going to tack on that negative sign there. Now from superposition, we can consider the bound volume charge density added to, the real charge density, or, the rho v. And actually this can dramatically influence the resulting electric field, the polarization, that is, this bound volume charge density. So what we have then is that from Gauss's law, the divergence of E now right, we've added the bound volume charge density to the real charge density, or the usual charge density. And remember, we've got I think our original form of this equation was the divergence of D, but remember D and E are related by epsilon 0 since this material is in free space. So I can write this now like this: rho v minus the divergence of the polarization, like this. Or if I rearrange some things, I've got del dot epsilon 0 times the E field plus the divergence of the polarization equals rho v, or the divergence of epsilon 0 times E plus the polarization equals the volume charge density. And then remember, then what we're going to do is we're going to redefine D. Recall at the beginning of our talk of materials, the electric field of materials, we said we're going to need to modify some equations. So now what we're doing is we're modifying the definition of electric flux density D. So let me erase some of this up top. We're changing the definition of electric flux density. In free space, we said that the electric flux density was epsilon 0 times the electric field. Epsilon 0 was the permittivity of free space. Now you can see from my work down here in the bottom right that we're defining D as this thing in parentheses. So now we're changing the definition, not in free space anymore. We're changing the definition. We see that the free space was just a specific case of a more general case in which there's polarization inside the material. So the net effect of the dielectric on the electric field is to increase the electric flux density inside it by the amount of polarization. Now, for some dielectrics, I'll just say for some dielectrics, the polarization is proportional to the electric field. So what we would have is the polarization would be some proportionality constant, which we'll call c sub E times epsilon 0 times the electric field, right? So again, the polarization is proportional to the E field, and we call this c E the electric susceptibility of the material, or of the dielectric. So now, if that's the case, if the polarization is proportional to the electric field, then we have from this equation that the electric flux density, the total electric flux density, is from the original field, right, plus the part due to the polarization, and the electric field and epsilon 0 can be factored out. The electric field and the permittivity, that is, can be factored out like that. And what we can do is then call this thing, in parentheses, we're going to call that epsilon r. And then, if that's the case, we now have a form that we like, where the electric flux density is just epsilon times the electric field, where epsilon is the permittivity of free space times this epsilon r. Right? So you see we've modified our original equation that I crossed out up here. Originally in free space we said that the electric flux density was epsilon 0, the permittivity of free space, times the electric field. Now we're saying that the electric flux density is epsilon times the electric field. So what is epsilon? Well, epsilon r is what we call the relative permittivity. So the r stands for relative, and you see it's a fraction of the permittivity of the material versus so epsilon is the permittivity of the dielectric. So it's the permittivity of the dielectric versus the permittivity of free space, and that's why we call it the relative permittivity. All right. So that gives you a sense of the polarization in dielectrics, and we're going to continue our study of electric fields in electrostatic fields, that is, in materials.